عمر بس.
دكتور هل بيكون في normalization للكوزات بعدين ولا شلون؟
Yeah, class 4 could be normalized إن شاء الله.
How much will be the percent?
Don't know yet.
Okay, thank you.
بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome to E21. So today's lecture will be the 22nd. So before starting the lecture, I just want to point something out. It's very important. Shabab, when we have a quiz or whatever, I mean, or whenever we have a quiz, if the quiz is written, it means that I care more about how you find or how you reach the final solution more than actually the final solution itself. So there's some occasions where some circuits, if you use a wrong approach, you will end up with the correct solution. And an example of this is what we had in quiz 3. But this does not mean because you got the correct solution does not mean that you should get full credit out of it. It means that yes, you used the wrong approach, and it happened that the circuit was kind of like the circuit allowed you to, or this type of circuit can be solved using this wrong approach. If I care about the final solution, I would give you a multiple choice question, something on Blackboard, because it will not take me more than a few seconds to complete grading. However, asking you to upload your solution takes about like an hour and a half to finish all gradings. But it's very important. Getting the right solution, getting the correct solution is not it's not something that's going to stick with you when you finish this course. It's like the way you think about things, the logic behind things, and like the concepts behind these mathematical analysis that we will use is what's going to be useful for you after finishing this course. Okay, so before we start, there's a few announcements. So the first one is homework is posted, and inshallah it's due Wednesday at 11:59. I don't mind if you want to postpone it, if you want this homework to be postponed till Thursday, but Thursday is an official holiday, so I don't want to make any deadline during holiday. Quiz 4, inshallah, is on Wednesday. The coverage for this is chapter 7, 7.7 to 7.6. Any question about the logistics of the course before I start? طيب. طيب. I know that last week was the midterm, so I would assume that 80 to 90% of you did not pay attention to what we did after that. After chapter 4, because chapter 4 was the last thing in the midterm. So in order to put everyone on the same page, I'm going to I had two options. The first one is just continue the flow of the course as it is, following the syllabus. The other thing is actually to pause for 20 minutes and try to recap or try to like represent the fundamental things that we studied in chapter 6 and 7, and the very first part of chapter 8. I chose the second approach because it's very important that everybody is on the same page, and you kind of like know exactly what we're doing and where we're heading. So let's start with what we did in chapter 6. So if you remember, we talked about the first thing we talked about inductor, and so if you're reviewing the material on a daily basis, maybe this is something boring for you. So just bear with me for 15 to 20 minutes. If you're not, this is your chance to actually get up to speed with what we did. So the symbol for the inductor is something like this. The voltage, V, L, and we have the current following the passive sign convention. So the voltage in the inductor is given by L, which is the inductance, the derivative of time with respect to the derivative of the current with respect to time. So there are a few notes that are worth mentioning. The first one is inductors actually store magnetic energy. This concept will be very important when you take AE340 or 605. The second important thing is current passing through an inductor cannot change instantaneously. However, voltage can. Voltage can change instantaneously. As a matter of fact, if you have an inductor that's been like connected to a source for a very long time, or connected to a source for a very long time, then you all of a sudden you remove the source, you see there is an abrupt change in the voltage. The third important thing is like the energy stored in the inductor is 1/2 inductance multiplied by the current. This again derived by integrating the power with respect to time. So that's what we did with the inductor in chapter 6. Then we moved to capacitor, which is another energy storage element, and almost the analysis is almost the same compared to the case of the inductor. The only difference is there are few differences here. The first one is the symbol for the capacitor. So capacitor is drawn like this. Here, the current in the capacitor is given by the capacitance multiplied by the time derivative of the voltage with respect to time. Again, there are a few notes. So the first one is capacitors store what type of energy? Electric energy. The second thing is actually voltage across a capacitor cannot change instantaneously, compared to the case of the inductor, and the inductor current passing through the inductor cannot change instantaneously. The third and last thing is actually the energy stored in the capacitor is related to the voltage and the capacitance. Okay, that's basically what we did in chapter 6. We studied the capacitor and the inductor, and we kind of like studied again the parallel and series combination of capacitor and inductor. We saw that the inductor behave a lot like a resistor when we combine them. So if they are combined in parallel, you add the individual inductance. If you combine in parallel, you take the harmonic mean. If they are connected in series, then you sum them up, you sum the inductance up. Capacitors are the opposite. There are a few exercises in the book. I encourage you to actually go over there and try to study. Then, after introducing these circuit elements, we said, well, what happens if we have capacitor or inductor in actual circuit? So here we studied capacitors and inductor individually, how they behave, but the first sort of complication is, let's assume that we have an inductor and a resistor in a circuit. Let's study what's going on. Then we will do the same for capacitor. So let's study inductors in circuits. We have two cases. Case one. In this case, we are concerned about DC analysis. So the capacitor or the inductor being connected to a DC source for a very long time. And this is called DC analysis. We notice that, well, the inductor behaves like a short circuit. So if we have a short circuit, it means that the voltage across it is zero. This one is called the DC steady state. Okay, maybe this is not something interesting. The interesting thing is case B. Case B is what happens if there is an abrupt change, if there's a sudden change in the circuit itself. So you take this inductor and resistor in a circuit, and all of a sudden you connect or disconnect a source. So let's study what happens. And this is something this is more interesting than the previous one, the previous case, which is the capacitor of the inductor being connected to a source for a very long time. So we know what's going on. So case B, or case 2, we have a sudden change in the circuit by adding or removing a source. So this is called the transient response. Okay, this is the transient response of the circuit. And this is the most interesting thing here. It's not the DC part, it's the transient, it's not the steady state, it's actually the transient behavior. So you may ask yourself, okay, how to analyze this circuit? It's easy for us to analyze the circuit if it's in the steady state, because we know that the inductor behaves like a short circuit. So we can assume that inductor is a short circuit, the voltage across it is zero, then all what we have are resistors, and we know how to deal with them in chapters from chapters 1 to 4. Now, if we want to study the transient behavior, this is just like the few moments after adding or removing the source. Then we need special. Then this analysis needs special treatment. So let's raise this question: how to deal with a narrow circuit. So let's assume we have the following circuit. We have a voltage source. We have a resistor, we call it resistance, we call it R equivalent. We have a switch. T equals to 0, the switch is closed. Then we have this inductor. And clearly here, the most important thing is actually finding the current passing through the inductor. Because if you find the current passing through the inductor, you can easily find the voltage across the inductor. You can easily find the energy. You can easily find the power. So remember, our ultimate goal is to develop an expression for the current passing through the inductor. And this expression should account for this kind of like abrupt change in the circuit itself. So we don't want to count only for the extreme values. So what happens when the switch has been open for a very long time, or what happens when the switch has been closed for a long time? Because we know for sure here, looking into the circuit, the current will be exactly Vs divided by R equivalent if the switch has been closed for a very long time. If the switch has been open for a very long time, then the current is exactly 0 because we have an open circuit. But let's study what happens from the moment you close the switch to something called few time constants. So in order to deal with such a circuit, we need to develop or devise a kind of like a systematic way of solving for the current. So the first thing is we need to find R equivalent. Here we represent everything in terms of like a single resistance, but in some of the circuits that we studied, we had a situation where we have combination of resistors. So the very first thing is we need to find the equivalent resistance between the terminals of the inductor. And this can be done from, or this resistor is exactly the Thevenin resistance. So we need to follow Thevenin analysis. Then once we found the resistor, we can find the time constant. Tau, which is L divided by R equivalent. Then once we found the time constant, we can find the initial value of the current, I naught. Notice here that you can start from any order you want. The only thing here is you cannot find the time constant unless you find R equivalent, but actually you can find the initial value of the current without or before finding the equivalent or before finding the time constant. So the initial value of the current, I naught, which is when T is less than the switching time. So here I will be very precise, and I would say that T equals to T naught. So at a specific time in an instant, this is what happens. The switch has been closed. So we need to study the situation or the find the initial current before the switch has been closed. The last step is actually we need to find the final current. I final. This is by taking the limit as t approaches infinity. So the switch been closed for a long time. Everything now is in its steady state. So we need to actually, and we can easily find the current, the final current. Now, if I know all of these information, I can actually express the current as the following: I naught minus I final T minus T naught divided by tau. The unit is ampere, and this is true for T less than or for T greater than T naught. Okay, this is what happens when we study the transient behavior. As you can see here, if you assume T equals T naught, then you're getting the initial value of the current. If you're assuming T equals to infinity, then you're getting the final value of the current. So any question, Shiva? Okay, that's for the current. Let's see what happens when we talk about that's what happens with the inductor. So let's see what happens when we have a capacitor. So instead of actually reviewing or writing everything back, I'm going to copy all of these, and I'm going to modify it to account for the fact that we have a capacitor instead of inductor. Okay, the first thing I need to do is actually remove the word inductors and replace it with capacitors. So in the case of if we have a capacitor, then for DC analysis, the capacitor will behave like an open circuit. So if we have an open circuit, the current is actually 0. So here we have this is exactly called the DC steady state response. If there is a sudden change in the circuit by adding or removing source, then we have the transient behavior of our analysis or of our RC circuit. So now I'm going to do exactly the same. I'm going to ask the same question. So I will ask how to deal with an RC instead of RL circuit. So if we have an RC, means that a circuit that has a resistor and a capacitor, then in this case, the analysis is actually similar to the case when we have an RL circuit. There are a few differences here. First of all, the circuit will look like the following. And we are interested in finding the voltage across the capacitor. So the first thing is we need to find the equivalent resistance using Thevenin analysis. Then we need to find the time constant. However, the time constant is slightly different here, or it's completely different. So the time constant is R multiplied, or R equivalent multiplied by the capacitance. Then we need to find the initial value of the voltage, because remember here, we are interested, once you find the voltage, you can find every value you want. So we need to find the voltage. V naught. And we need to find here, let me modify it. And then I'm going to modify the circuit here. So it's exactly the same. So the only difference is the time constant and the fact that I need to care about or I need to consider the voltage, not the current. Any questions, Shabab? This concludes chapter 6 and 7. Okay. So now let's review what we had in chapter 8. If you recall from the last lecture, we kind of, like we said, well, in the previous analysis or in the previous chapters, we considered the case where we have either resistors by themselves, which are chapters 1 to 4, or a resistor and an inductor, chapter 7. Resistor and capacitor is also chapter 7. So now let's study what happens if we have actually the three elements here: the resistor, the capacitor, and the inductor. And the analysis is slightly different if you have parallel or series combination. So let's start with the parallel combination. In this case, if we have a parallel combination, then the common element or the common quantity among these three elements is actually the voltage across the capacitor. And if we apply KCL and kind of like do some mathematical manipulation, if you refer to the analysis last time, you will see that we will end up with this differential equation. So this differential equation relates the second derivative of the voltage to its first derivative and to its zero derivative. So it turns out the solution of this problem has the following form: A1 e to the power s1t plus A2 e to the power s2t. So we notice that, well, A1 and A2 are determined from the initial conditions. So what are the initial values of the voltage and current across the capacitor? From these initial values, we can actually find A1 and A2. Now, what about S1 and S2? It turns out that if you take this solution, or if you take, say, for example, EST, this is the general solution, you take it, substitute it here, you will see that in order for this differential equation, in order for the left-hand side to be equal to 0, you have to ensure that this quantity is equal to 0. And this is called the characteristic polynomial. So in order for this polynomial to be 0, its roots, there's some certain allowable or certain permissible roots. And those roots are following called characteristic roots, S1 and S2. S1 depends on alpha. Alpha is 1 over 2 RC. And omega naught is 1 over square root of SC. You see that S1 and S2 depend on the circuit elements, on the values of the circuit elements, R, C, and L. A1 and A2 depend on the initial conditions, the initial value of the voltage and the initial value of the current. So it turns out, depending on the relation between alpha and omega naught, we have three different situations. The first one is something called overdamped. The second one is critically damped, and the third one is underdamped. So in order to differentiate between overdamped, critically damped, or in order to understand the underlying concept here, think about overdamped is kind of like, well, there's a final value that there's a final value that the voltage must reach, which is 0. No matter where you start, the final value should be 0 here. So the issue here, or the three situations. It could decrease slowly until it reaches 0, and this is called overdamped. It could decrease quickly to reach 0, and it could oscillate, as well as while it oscillates, it's kind of like its amplitude, its magnitude is decreasing. And this is called the underdamped response. So we start with, well, if you are designing a circuit, then the best response you have, or if you are designing a circuit, then you're aiming for actually critically damped. Because if you want to close the switch, imagine here you have a switch. There's an initial value of the voltage, you're connecting a source, then you immediately disconnect the source. So what you want to see is that you want to ensure that the voltage is actually zero when you disconnect the source. So you don't want to actually imagine that you have a device and the device is connected to a battery. So you don't want when you disconnect the battery, when you turn off the device, that the device is been running for a while. You don't want this before it's actually completely shut down or shut off. So this could be achieved if you have critically damped response. However, you see that with critically damped is actually on the verge between underdamped and overdamped. So when we talked about underdamped, we were talking about some sort of oscillation. So yes, eventually it's going to be zero, when the voltage will be zero, but it's going to be oscillating here. Could be, for example, if the initial voltage is 10 volt, then you will see that as time time passes, you see that it kind of like decreases to something between 8 and -8, then 6 and -6, then 2 and -2, 1 and -1, etc., until it eventually reaches 0. So in the last lecture, we started with the overdamped voltage, and we saw that in order to actually study overdamped response, there's some systematic way of actually tackling the problem. The first one is you verify that the response is overdamped. So you find alpha, you find omega naught, and you ensure that alpha is greater than omega naught. Once you find alpha and omega naught, you can easily find the roots, S1 and S2. You see that S1 minus alpha, S2 and you know alpha is 1 over 2 RC, omega naught is 1 over square root of L multiplied by C. Okay, now you found S1 and S2. So these two are found. So what about A1 and A2? So in order to find A1 and A2, like we said previously, you need to study the initial value of the voltage and the initial value of the current. So if you substitute the value of the voltage, if you substitute this value to be 0, if you substitute it with a 0, then you will get the initial voltage, which is in this case V0, and V0 is equal to A1 plus A2. If you take the derivative of the voltage with respect to time, you will get the current passing through the inductor divided by the inductance, because remember, I is C dV by dt. And here we're concerned about the voltage across the inductor. So dV by dt is actually I divided by C. Any questions about it? Okay.
Yes, doctor. When we substitute with 0 in the voltage to find A1 and A2,
Yes.
don't I need an equation to substitute in to, like, how can I don't know the value of V to substitute the 0. So.
Yes, you know that. You should know that from the initial value of the voltage across the capacitor.
Oh, yeah, okay. So this is just a V0, just the initial value. Okay, thank you.
Yes. Any other question? Okay, good. So let's illustrate this problem with an exercise. So in this circuit, we have a parallel RLC circuit. We have an inductor, a capacitor, and a resistor. And we're told that the initial value of the current of the voltage across the capacitor is 12 volts. and the current passing through the inductor is 30 milliamperes. So we're given the initial value of the voltage, we're given the initial value of the current, because we know that the value of the current cannot pass through the current passing through the inductor cannot change instantaneously. The voltage across the capacitor cannot change instantaneously. So what we want to do here, what we are asked to do, the ultimate goal is actually to find the expression of the voltage. But this is the first exercise in this concept. So it's kind of like walking you through the process. So it's asking you to find the initial value of the initial current in each branch current. But before that, let's verify. Let's verify, since we're talking about overdamped response, so let's verify that this response is actually overdamped. So how to do that? Karim?
I need to find alpha and omega, and alpha is 1 over LC.
1 over
1 over 2 RC.
So R is 200, and C is 0.2 micro. So it's going to be 1 over 2 multiplied by 200 multiplied by 0.2 times 10 to the power negative 6. And this is going to give me 1.25 times 10 to the power 4 radians per second. Now I need to find alpha squared. So if I square it, I will get 15625. What about omega naught, Ibrahim?
It is 1 over square root of LC. But since we're squaring it, we can.
Okay. Salman? So now, what should we do?
We need to find S1 and S2.
No, but before that, we need to ensure that
Alpha is greater than omega.
Which is the case, right? Alpha is greater than omega naught. We have 1.5 multiplied by 10 to the power 8 versus 1 multiplied by 10 to the power 8. So in this case, overdamped. So the response is overdamped. Okay. So that's not what we were asked about, but it's really good to keep this in mind. So what we are asked about is the initial current in each branch. So what's the initial current in the inductor branch? Anyone? Rahim?
It is given in the question.
Okay, exactly. What about the resistor branch? Anyone?
We can use Ohm's law.
Yes.
12 over 200. Exactly.
For a resistor, it's going to be V0 plus, which is given to us, divided by R using Ohm's law. So 12 divided by 200. This is going to be 60 milliampere. Again, for the inductor is actually 30 milliampere. This is given. So what's remaining is actually the current through the capacitor, the initial value of the current through the capacitor. So what is the initial value of the current, or how to find the initial value of the current for the capacitor? Anyone? Mohammed Aswani?
Yes, we use KCL.
We use KCL, exactly. So I see by KCL, it's going to be minus this is going to give me minus 90 milliampere. Okay, so now I found the initial value of the currents in each branch. Now I need to find the initial value of dV by dt. So basically what I need to do is actually dV 0 plus by dt. So what is this initial value? What does it depend on? Walid?
Depends on I over C.
Yes. This is exactly like this. So IC 0 plus divided by C. So in this case, I'm going to get minus 90 minus 450 kilovolt per second. So this is the value. Okay, now I'm done. So I need to find the expression for the voltage. So in order to find the expression for the voltage, first of all, I know this is overdamped. So V of t is going to be something like this. So what I'm missing here is actually A1 and A2, S1 and S2. So let's start with S1 and S2. So how to find S1 and S2? Okay.
I need S1 will be minus alpha plus the square root of alpha square minus omega square.
Which is, you solve for it, you will get 5,000 radians per second. S2 would be the negative square root. You solve for it, you will get minus 20,000 radians per second. Okay, so now I found S1 and S2. What's left is A1 and A2. So what should I do? Yasser?
Yes, we equate IC over dt, the one that we calculated, IC over C. We equate it by AS1 plus AA1 S1 plus A2 S2.
Yes, we can do that, and we can also.
We need another equation, so we can write another equation which is A1 plus A2 equal 12.
Yes, this is the first equation. The second equation is again, this is S1. This is S2, and it's equal to 450 times 10 to the power 3. So if I solve for it, at this stage, we know how to solve for it. We know how to solve a system of equations. So it's not something that we need to spend time on it. We can do it with a calculator. We see that A1 is minus 14 volts. A2 is actually 26 volts. So the expression for the voltage is minus 14 e to the power minus 5,000 t plus 26 e to the power minus 20,000 t. The unit is volts, and this is true for t greater than 0. Any question, Shabab? Okay, very good. You see how simple this analysis. That's a good thing about chapters 7 and 8. They kind of like they have a systematic way of solving problems. It's not complicated. Plus the underlying concept is really interesting. Right. Question 4 is asking us to find, to sketch VT in the interval from 0 to 250 milliseconds. Well, I kind of like, I'm not the best artist here, so I would sketch it in a way acceptable to me. But the complete picture is actually shown in the book. So it's something like this. You see that it will start with 12 volts, then it will decrease until it reaches 0, then it will saturate. It will decrease until it reaches 0, then it will increase. It will decrease below 0, then it will. If you progress in time, you will see that it will be 0. Okay. Any question?
Doctor,
Okay.
could you go back to the previous slide?
Sure.
Isn't it equal, dV over dt, isn't it equal to negative 450?
Yes, it's equal to negative. Yes.
Okay.
Thank you. Okay, very good. So this is the first case. What about the second case, the underdamped voltage? So in this case, underdamped response takes place when omega naught is greater than alpha squared, or omega naught is greater than alpha. So what happens to the roots? So remember, S1 is written like this. You will have something like this. And before that, let me. If you recall, this is the critical quantity here. We have alpha squared minus omega naught squared. Since omega naught is greater than alpha, you will see that the quantity here is less than 0, which means that you have a square root of something negative, and in this case you have an imaginary part. So what we can do is we can take -1 as a common factor. Then the square root of -1 is, in our case, J. Remember, here in electrical engineering, we use J to represent the complex, the imaginary number, compared to people in mathematics or physics, where they use I actually to represent the complex number. Because I here in the electrical engineering is reserved for current. So minus alpha plus. Or in this case, we can write that omega d is actually S2 will be the complex conjugate of this one. So the complex conjugate for any complex number is when you take the real part and keep it as it is, you take the imaginary part and you negate its sign. So omega d is called the damped radial frequency. So if you recall, we have the solution is E ST in this case. You will see that A minus alpha t, then A plus or minus omega d. We'll see inshallah in chapter 9 that if we have something like this, then it can be written as cosine alpha plus j sine alpha. There's some mathematical simplification. I'm not going to deep dive into it. But the long story short, the solution will be of the following form. So we have B1 e to the power minus alpha t, B2 e to the power minus alpha t, and then there is a cosine and sine, and it's those cosine, it's those sine and cosine that are responsible for this oscillation or fluctuation. So alpha is called the damping factor or the damping. In order to find, well, we know how to find alpha, we know how to find omega d from the circuit elements. In order to find the B1 and B2, so the initial value of the voltage is B1. The derivative or the initial value of the current divided by the capacitance is related to, can be used also to find the value of the constant B1 and B2. If we take the following circuit or the following equation and try to plot it, you will see it's something. Let's take one component here. Let's take this component. If we plot it first time, you will see that this is a cosine term. So it should be something like this. You will see that if you plot this one, you will see that this one is equal to e to the power minus alpha t. This one, it's negated version. So e to the power negative alpha t is what's keeping this omega, what's kind of like what's damping or what's concentrating the response, or what's ensuring the response, that the response is actually eventually reaching zero. It's not omega d, it's not this term, cosine omega t or sine omega d. Those are oscillating terms. If you take them by themselves, you'll see that this is the cosine term. But since you multiply them by a decaying exponential, this decaying exponential will force the response to be eventually zero. Any question, Shabab? And this was what makes it physical. Okay, let's try to solve this exercise. Again, in this case, if we have an underdamped voltage, we are going to use the same or underdamped voltage response. We're going to use the same approach that we did with overdamp. The only difference here is we need a different form of solution. That's the only difference here, and different initial conditions. Okay, but again, the very first step is to verify that this is an underdamped response. So we have the same circuit like before. We changed some values. In particular, I think we changed the value of the resistor, and I believe the inductor was also changed. Yes, the resistor and the inductor are changed. So first of all, we want to calculate the roots of the characteristic equation. First of all, we need to understand what kind of, because if we have an overdamped response, then in this case, the roots are real. If we have an underdamped response, the roots are complex conjugates. We have two roots and they're complex conjugates. So let's first of all, let's verify that this is an underdamped response, or this is an underdamped circuit. So how to do that? Okay, let me see. Ali?
First, we calculate alpha and omega naught.
Yes, exactly. So we need to calculate alpha and omega naught.
Alpha will be equal 1 over 2 RC, which equal to 1 over 2 multiplied by 20 multiplied by 0.125 multiplied by 10 to the power minus 9.
Exactly. So this one will be 200 radians per second. Omega naught is 1 over square root of LC. And if we we're going to get 10 to the power 3 radians per second. So we can see that omega naught is greater than alpha. So it means that omega naught square is also greater than alpha square. So the square root is going to be negative. And this case is called, the response is underdamped. Okay, if we have an underdamped response, then we know that the root is 1 and is 2, then minus or plus J omega d. So we know alpha. All what's left is to find omega d, and omega d is omega naught square minus alpha square. And if we do that, we'll get 10 to the power, or 10 multiplied by square root of 96, or I'm sorry, 100 multiplied by square root of 96, or 979.8 radians per second. So S1 will be minus alpha plus J omega d, or minus 200 plus J 979.8 radians per second. S2 is minus alpha minus J omega d, or minus 200 minus J 979.8 radians per second. Any questions, Shabab? Do you have any question? Dalla, question?
No, I want to participate.
Okay, so yeah, let's go for part 2. So what's part 2? Part 2 is asking us to calculate V and dV by dt at t equals to 0.
I think it will be 0.
Yes, for V is going to be 0. Okay, what about dV by dt? What about dV by dt, Shabab? Kareem?
Can I check IC 0 over C?
Yes, IC over C. What is IC?
Minus 12. Isn't it minus 12.25?
Yes, it will be no. It will be plus 2 minus this one.
Yeah.
Okay. So dV by dt. So you may ask yourself, what is IC? So in this case, IC by KCL is going to be minus IL minus IR. So we know IL from the question it's given to us. What about IR? IR by Ohm's law is V divided by R, but V here is 0, so IC is going to be just negative IL. So dV 0 by dt is going to be IC 0 divided by C, which is 9.8 kilovolts per second. Okay, so now we found the initial value of the voltage and the initial value of the derivative of the voltage at t equals to 0. So now we are asked to find the voltage response, V of t. But we know here that, well, we have an underdamped response. So the expression for the voltage is something like this. Vt B1 E minus alpha t cosine omega d t plus B2 E minus alpha t sine omega d t. So this is the voltage response. So we know omega d, we know alpha. We're missing B1 and B2. So how to find B1? Yes, sir.
For B1, it will be V naught plus V0 plus, and it will be 0.
Exactly. So B1 is 0. What about B2, Ziad?
B2 will be IC over C also over the.
Yes. Just give me, I will give you. Since B1 is 0, so B2 will be simply dV by dt was 98 kilovolt. So B2 will be 98 kilo divided by omega d, which is 196, and this is going to give you approximately 100 volts. So the response is going to be the unit is volt, and this is true for t greater than 0. So this is what happens if you so this one is 100 multiplied by minus 200 t, and this one is actually minus 100. Any question, Shabab? Okay. We covered the overdamped response. We covered the underdamped response. What's left is actually the critically damped response. And for critically damped response, we have alpha equals to omega naught. So in this case, S1 and S2 are identical, and they're equal to minus 1 over 2 RC. And in this case, the solution will be of the following form: D1 e to the power alpha t plus D2 e to the power negative alpha t. So in order to find the constants, well, alpha could be found easily from the circuit. D1 and D2 is actually can be found by substitution. So the initial value of the voltage is equal to D2. The derivative of the voltage, or the current passing from the inductor, is divided by its the current passing through the capacitor divided by its capacitance, can be used to find D1. Okay, so let's see what we have here. We have exactly the same circuit. Okay, there's some issue here. Let me make sure I can. Okay. Okay, R here is not 20 kilo ohm. We are asked to find what value of R that ensures we have critically damped response. So in this case, so let me make sure that. So R is missing here. So what value of R that ensures a critically damped response? So what should I do here? I'm given C, I know C, I know L. What can I say about, or how to find the value of R such that I have critically damped response? Mohammed?
Can I say 1/2 RC equal omega?
Yes, exactly. So 1/2 RC equals to omega naught. So this is exactly the same circuit before. The only difference here is R is missing. But omega naught does not depend on R. Omega naught depends on L and C. So from the previous exercise, omega naught is 10 to the power 3 radians per second. So we need alpha to be equals to omega naught. So in this case, 1/2 RC should be equal to omega naught, which is 10 to the power 3. In this case, R is 4 kilo ohm. So if R equals to 4 kilo ohm, you will see that the response is critically damped. If R is actually less than 4 kilo ohm, then the response will be overdamped. If R is greater than 4 kilo ohm, the response is actually underdamped. So R equals to 4 kilo ohm is at the edge, or at the verge between, or on the verge between critically damped and overdamped. Okay, we found the value of R. Then we are asked to calculate Vt for t greater than 0. We know that this is critically damped response. So V of t is actually D1t plus D2 e to the power minus alpha. So I know alpha. I calculated it. It's equal to omega naught because I have a critically damped response. So let me calculate D1 and D2. So D1 can be found using the initial value of the, D2 can be found using the initial value of the current of the voltage. So in this case, remember we're given D2 equals to, we're given V2 equal, V naught equals to 0. So this one is actually 0. D2 is equal to 0. Now, in order to find D1, I need to find the current passing through the inductor here. And it happens that because it's exactly the same circuit, the initial value of the voltage is exactly the same. So the dV by dt is equal to dV by dt from the previous exercise. If you're not sure, then you have to double check. But the only difference between this circuit and the previous one is the value of R. But remember here, IR is equal to V naught divided by R, which is 0 divided by R, which is 0. So as long as V naught is exactly 0, the initial value of the derivative of the voltage with respect to time is identical to the previous one. So D1 will be 98 kilovolt. So the expression for the voltage is then something like this. The last part is asking us to plot Vt versus time, and this might be better to do it to refer you to the textbook here. But just for a quick plot, it's going to be something like this. So it will start with 0, then will decay. But again, you need to refer to the textbook when it comes to that. We have 3 minutes, and in these 3 minutes, I want to summarize what we did. Okay. So overall, what we did here was actually, there's some unique steps here. So the steps in calculating the response for the natural response for a parallel RLC circuit, we have, first of all, we want to calculate alpha and omega naught. You can do that by, you can find the values of alpha and omega naught from the circuit elements. Then you need to ask yourself, is alpha greater than omega naught, or alpha squared greater than omega naught? Then in this case, the response is overdamped. Is alpha naught squared less than omega naught squared? Then the response is underdamped. Is alpha naught squared equals to omega naught squared? Then the response is actually critically damped. So you calculate alpha and omega naught, then depending on the ratio between alpha and omega naught, you can deduce whether the response is overdamped, underdamped, or critically damped. Then you calculate this one and this two. Notice that if you have critically damped, then S1 and S2. If you have underdamped, then S1 and S2 will be complex, and those are equal to So now you know the roots. Once you know the roots, you can, well, now we have everything to write the solution, to construct the solution. So if overdamped, Shabab, feel free to leave if you want. It's going to be recorded. Just want to summarize this before we conclude. A1 S1T plus A2 S2T. If underdamped, then the voltage will be B1 E1 alpha T cosine omega dt plus B2 Finally, if it's critically damped, D1T E minus alpha T plus D2 E minus alpha T. Okay, so now we construct the solution. So let's summarize how to find the constants that depend on the initial conditions. So the last thing is actually if A, which means if the response is overdamped, then V0 plus equals to A1 plus A2, which is equal to the initial voltage across the capacitor. The derivative, the initial derivative of the voltage across the capacitor with respect to time is equal to the current, the initial current of the capacitor divided by the capacitance. And in this case, it's going to be equal to S1 A1 plus S2 A2. If you have critically, or if you have an underdamped response, then in this case, B1 equals to V naught, initial value, divided by C, and it's going to be alpha B1 plus omega D V2. And the last thing is you have critically damped, so the initial voltage is equal to D2, and the derivative of the voltage, which is equal to the initial current divided by C, and this is equal to D1 minus alpha D2. Okay, that's all. Thank you very much. We'll see you inshallah tomorrow. Any questions, Shabab? Rahim?
Doctor, for S, isn't it different for underdamped? S1 and S2.
It's going to be exactly the same. The only difference here is one of what is going to be complex. So if you take if alpha, if you have underdamped, then you have the negative square root. So the solution for this one is J. Then you take that
Alpha square minus alpha square.
Good. Yes, sir.
Thank you.
Sure.
Doctor, will we be given a formula sheet like this in the exam?
Inshallah, I'm not sure if it's going to be like this, but for the quizzes, you will not be given, as far as I know. Or up until this point, I might give you a formula sheet for the quizzes, but not for quizzes and for the final for sure. Okay, Ziad?
For the underdamped voltage,
Yes.
isn't it minus B2?
minus B2. No, it should be minus alpha B1 plus omega D B2. Let's double check. No, it's minus alpha B1 plus omega D B2.
And are you available for office hours today?
Inshallah.
Okay.
طيب, no other questions? Okay.